Hi, I'm Ben-Yaakov. This presentation is entitled Current Sharing in Highly Parallel MOSFET and IGBT Transistors. There is a relevant video to this presentation. Here is the link, and I'm going to print the link in the description section of the video that you are now watching. So the problem that I'm addressing in this presentation is paralleling transistors, and the question is, what is the distribution of the current in this arrangement? Now here is a half bridge, could be for an inverter of an inverter, and in the case that one transistor cannot carry the full current of the phase, and even if it's a large transistor, then the practice is to put a number of transistors in parallel. Now, this is MOSFET, and these could be IGBTs. So we have a large number, or could be a large number of transistors, like 5, 6 transistor in parallel in order to increase the current capability of the inverter. Now, the question is now, if I have this connection in parallel, if I look at one particular transistor, say this is this transistor under test, let's call it, then the question is, what is the current of this one as compared to the current of, or the average current in the other transistors? Now we know that there is a spread in the parameters of the transistor. If you look at the data sheet, there is a spread. I'm going to show it and discuss it later on. And due to this spread, there is no question that the current will change. It will not be the same for all of them. So if I assume that there is sort of an average current here for each of one of these transistors, this transistor might have a different current, it's a deviation from the current, and this will be accompanied with a deviation of the temperature. I'm assuming that all the transistors are clamped to the same heatsink. However, the junction temperature may not be the same, because the junction temperature depends on the current first of all, and then on the thermal resistance between the junction, the case, and perhaps there is a thermal pad between the case and the heatsink. So this delta T depends on the drop of the temperature drop between the junction and the heatsink. So the objective of this presentation is to see what is affecting this deviation of the current, how much will it be, can we estimate it, and the deviation of the temperature. Now let me say that this presentation does not provide a mathematical solution or numerical solution to the problem in an accurate way. The objective here is just to understand what is affecting these deviations. What are the processes? What are the parameters relevant? I think that the best way to study a practical case is to do simulation. For that, you need a good model of the transistor, and then you can run a simulation and see what will be a deviation if you change the parameters. However, it is important to understand what is affecting it, so that if you look at the data sheet, if you see the spread of the parameters, you can sort of estimate how severe is the problem of unbalance, or whether it's not that bad. So this is the objective of this presentation. Also, I'm not going to dwell into the situation in which you have, let's say, an inverter, and then you have a chopped current. So current is in one half cycle positive, and then actually it's negative. It's going through the diode. In the case of the inverter, if it's the low side, say, of an inverter, of a half bridge of an inverter. And I'm not going to look at this and to analyze it. It's very complex, and this is not the objective of this presentation. The objective is really the understanding, and for that I'm assuming a constant voltage here, okay? That's not realistic. So you might say I'm talking about the average voltage, say, due to this waveform of a current in practical cases. So we are talking about an average current, so I'm not talking about reverse current, which are passing through diodes, not through the IGBT. This is why in such a case you're going to have a IGBT with the diode inside or outside in order to allow for the reverse current. So I'm not going to dwell on that, just to talk about the transistor itself. So the first thing to do is to look at the specification and to look at the output characteristic of a IGBT. I'm starting with an IGBT. Later on, I'll talk about a MOSFET. And this particular IGBT is a 650 volt, 75 amp IGBT. And here I have two plots here, one for 25, one for 150 degrees centigrade. And let's have a look on the behavior, which is kind of very interesting. Not everyone is really aware of the situation that is usually happening, and that's the following. If I look at the voltage, this is VCE, the voltage across the transistor, and then the collector current, okay? So this is the voltage and this is the current. So if I look at the 0.5 volt, here I have almost zero current, okay? And here it's already 3 amp at the 150 centigrade. Now at 1 volt, it's 8 amp, and here it's 10 amp. So in this case, the current at 150 centigrade is higher than the current at 25 degrees. But look at this. At 1 amp here, it's 50, and here it's 1 amp, it's 35, so it's lower. So it's sort of swinging the direction. And then at 2 volt, it's 70 amp at 150 degrees and more than 100 here. So at the beginning, we have a current here, which is lower than the current at the high temperature, and then it is reversed. Now, to see it better, it's good to plot the two on one sheet here. And this is done by some manufacturer. Unfortunately, it's not done by MCC, so I'm going to do it myself. And what I'm going to do is to take the points, and I'm assuming a hard drive. That is that we are already at this line, which is sort of an average line for voltage, gate voltages above, say, 10, 12 volt. It's almost one line here, and also here about, 15 volt, it's one line here. So I'm just talking about this line here and this line here, and I'm plotting them on one sheet here, and here it is. So these are the two curves for 150 degree, 25 degrees centigrade, VCE, IC, and you can see here is a change in direction. Here, 25 degrees at a given voltage is higher, the current is higher than in the case of 150 degree, and here it's reversed, okay? So it's kind of a phenomena that is, you can see it in IGBTs, you can see it also in MOSFET, in fact, and the cross here could be here, and it could be much higher, which is very bad, we'll see that. So having it at a low current is better, and I'll explain it later on. So if I look at one particular operating point, say it's 1.5 volt over the VCE, then I can see here that the difference is 20 amp, okay? So between 25 and 150 degrees, 20 amp difference for this 125 difference in temperature. So now I can calculate this coefficient, which is a change in current as a function of the temperature, and I'm assuming sort of a linear relationship here. So 20 divided by 1.25, it's 0.16, and it's minus, because the current is going down as the temperature going up. This is very important, because this means that the system has, in fact, a negative feedback. If you have a temperature that, say, momentarily goes up, the current goes down, and this will cool the IGBT. So this is a negative feedback, which has the effect of actually reducing the changes and stabilizing the system. We'll see it in a minute in the next slide. Here, because of the change in behavior, we have positive feedback. luckily, the deviation here is much, much smaller. Now, positive feedback can lead to what's called thermal runaway, and that is the following. Suppose I'm at this point here at 25 degree. Suppose there is a increase in temperature. This will increase the current here, and this current will increase the temperature, and so on and so forth, and it could run away. However, just having positive feedback does not mean that you have a situation of a runaway, and I'll talk about it later on. So let's have a look now at some parameters that MCC is providing for this IGBT, and in particular, the spread of this VCE. So what I see here is that the maximum value is 1.95 and the typical is 1.65 volts. So it's about 0.5, that's, I'm exaggerating a little bit, deviation that you would expect between, say, one unit and another. So if I look at the deviation, the expected deviation, 0.5 volt, and it is specified for 75 amp. Here it is, this is specified 75 amp. So they say the normal or the average or the typical value will be here, but the maximum will be here according to the data sheet. So I can sort of draw a line for this IGBT, which is different from the typical. So this represents the IGBT that has this maximum value of VCE. So therefore, now the deviation between the typical and the maximum at this operating point, and this is the function of the operating point, it'll be different at another operating point. So if I walk here, meaning that the current that I'm talking about is 50, 60 amp, I see the deviation between the typical and the IGBT with this maximum value is 15 amp, okay? It's about 50. So the problem that we have is the following. We have a number of transistors in parallel which are sort of forcing a certain VCE. And then we have this transistor which is different. And the question is, based on the datasheet, what will be the current deviation and the temperature deviation? And I'm assuming that this transistor does not change VCE. So I'm assuming that although there is a change in the current, VCE is forced by these units. Now, in parallel, we have the thermal issue, and that is that inside this transistor, there is a power dissipated, which is the current times VCE, which I assume now to be constant. And this power with the thermal resistance develops a temperature difference between the heatsink and the junction. So this delta T is due to the deviation between the normal current and the current plus this delta I, and this will be now this temperature, the new junction temperature, riding over the heatsink temperature. This is a thermal equivalent circuit. I think that the best way to understand what is really going on here is to look at this system as a feedback system. We have a deviation of a current. This deviation times the voltage across the transistor, or just the IGBT, causes some power dissipation, which times the thermal resistance causes a change in the temperature. Now this change in temperature now times this coefficient that I have found is causing a change in the current back in a negative way, and this actually is sort of summed up with the initial forced change. So we have here a feedback loop. In this case, it's a negative feedback if we are above the cross point that I've shown on the plot. So we have a function here, which is the normal function of a closed loop, which is the A over 1 plus beta A. A is this term here, and beta is this term here. So if I put in these parameters, I find that the rise in temperature is a function of the native or inherent change in current times this term here, which is A, 1 plus this term here, and the expression for this difference, which will be the real current, because the real current is not the one that is expected without the feedback, but after the feedback is causing this change, which is subtracted from here. So this is the actual current that we'll see in the system. And this current now is, according to this equation, this original excitation and 1 plus the loop gain. So the loop gain has a very important effect here. Now, clearly, if the loop gain is very large, then the residual current that we'll actually see will be much smaller than the one that we have found from the open loop from the datasheet. Okay, this is like the datasheet open loop prediction, while this is the actual current due to the thermal feedback in the system. So now we can actually plug some numbers into these equations. So in our particular case, for the operating point that I've shown, this is the 15 amp delta I. This is the expected change without the feedback taken into consideration. I'm assuming a VCE of 2 volts. I'm assuming this coefficient between current and temperature of 0.16 minus 0.16 amp degrees centigrade. And I'm assuming the thermal resistance is 1 ohm. The transistor itself is 0.5, and then 0.5 for the thermal pad, so it's about 1 volt. So if I plug it in, I find that the temperature rise will be 23 degrees in this particular unit. Without the feedback, it would have been 30. So due to the feedback, we have an attenuation here of the change, and the same thing goes for the actual current. The original current would have been like 15 amp. This is without taking the thermal effect into consideration. And with the feedback of the thermal path, then we have 11 amp. Now, obviously, if this term will be larger, the number will be smaller. Now, this term here, which is this term here, is first of all something from the data sheet. This is the change in the current as a function of the temperature. Okay, depends on the transistor. Now, VCE, we'd like it to be small, obviously, to reduce the losses. And RT, we also like to have it small. So naturally, we like these numbers to be actually small. And if they are small, they don't make much of a difference. Okay, to make a difference, you have these numbers to be large, and this is something that you don't want. You don't want the thermal resistance inside the transistor to be very large. It will stabilize the system. Why will it stabilize the system? Because if the thermal resistance is large, then a small change in the current will cause a large change in the temperature, which will change, of course, due to this K, the current. So large thermal resistance is good in this respect, but we don't want large thermal resistance because it is increasing the losses. So the bottom line is that the negative feedback is indeed reducing the variation, both of the temperature and the current, but you wouldn't expect them to be very large because of the practical consideration. Now, from here, I'm moving to the MOSFET. So the story is the same thing, and I'm assuming here that the VDS here is constant, is forced by this transistor, and I'm looking at this transistor. Now, in the case of a MOSFET, the conduction is through actually a resistor, RDS on. It's not like a voltage drop, but rather a resistance. And then, of course, the temperature will go up when there is a delta I, and this story is exactly the same. There's no difference except that we have VDS rather than VCE, and then we have here a resistor. So it's really a different situation. Now, one way is really to start developing the concept from here. What I did is, first of all, to translate this situation to the IGBT case, okay? If I can translate this to the IGBT case, that it look in terms of the curves and the plots look the same, then I can use the same concept, okay? So this is the approach that I'm taking here. So first of all is, of course, to look what is the deviation you'd expect in the resistance. I'm talking about a transistor, which is 100 volt, 4.5 milliohm by Infineon. This is this transistor. And we see that the deviation is about 0.6 milliohms, between 3.9 to 4.5, okay? So this is the expected deviation. This is for current of, say, 64 amp. Okay, so then we have also the temperature dependence, and they are showing two curves, typical and 98%, the Gaussian curve. But let's talk about the typical. So I can take now two numbers, the 4 milliohm at 25 degrees, about 25 degrees, and the 5.8 milliohm at 125 degrees, that's about 125 degrees, and then plot this picture here, which assumes that the RDS(on) is independent on the current or the voltage across it. It's a straight line, just a resistor. So this is a resistor that ends up at 4 milliohm for 25 degrees, the 4 milliohm at 25 degrees, and this is 5.8 milliohm at 125 degrees. Now this picture is very similar to what we have with the IGBT. The current is a function of VCE, exactly the same. There we had this crossing. Here we don't see the crossing because I'm assuming here a linear resistor or resistance, 4 milliohm at 25 and 5.8 milliohm. So now if I assume that I'm operating at, say, 0.24 volt, corresponding to 60 amp, then I see that if the temperature will change between 25 to 125, then I'm going to have a change of 30 amp. So 30 amp divided by 100 degree, 125 minus 25, I come up with this coefficient, which is a very important one. It's a pivotal parameter here, minus 0.3 amp per degree centigrade. In the case of the IGBT, we had 0.16. Okay, here it's 0.13 amp per degree centigrade. So now I can also calculate what is delta I. Now the typical value at 25 degrees is 3.9 milliohm. Maximum value is 4.5 milliohm. So at 25 degree, the delta I will be 0.24. This is VCE divided by 3.9 milliohm, and then divided by 4.5, and the difference is 8 amp. So due to the change between the typical and the maximum value of the RDS(on) at a voltage of 0.24, I have 8 amp. So now I have exactly the same situation here. There is a change in the current due to the fact the RDS(on) is changing between the typical and the maximum. This basic change is now multiplied by the voltage to get the power, times the thermal resistance, we get the temperature change. This temperature change is now causing a change in the current per what we have found, and then this is going as a feedback. So it is exactly the same, except that the numbers for these parameters were taken in a different way. And this is not VCE, it is VDS. I'm just leaving this VCE here as the voltage across this, let's call it bus of all the transistors. So again, closed loop is A over 1 plus beta A, and this is exactly the same as before. So now we have actually all the information for one specific case, and I can plug in numbers, okay? Now we found that delta I is 8 amp. This is from here. We're assuming that we are operating at 0.24, this should be volts. Now, this coefficient between the current deviation and temperature is minus 0.3 amp per degree centigrade. I'm assuming again the thermal resistance of 1 ohm. Plugging it in, I get that the expected change after feedback of the temperature is 2 degrees because it's only 8 ohm, so it's 2 degrees. Now the loop gain is a very small number here, so it really doesn't make any difference. So therefore the loop gain does not change the actual values. So the temperature is just like in open loop. This is the open loop, and this is with this thing, which is the same. And again, the current, the delta E, like after the summation, but there is nothing to subtract because this value is very small. So it's 8 ohm. So in this particular case, because the loop gain is very small, it's 0.3, 0.24 times 1, it's much smaller than 1. The negative feedback, it does not make any difference. Now, in the previous discussion, we assumed that we are in this region both for the IGBT and for the MOSFET, of course, because the MOSFET is only this region here, in which we have a negative temperature coefficient here. That is, as the temperature goes up, the current goes down for the same VCE. Now here, it is reversed, okay? So we have to put here a minus. Now obviously we can understand when this comes to be 1, then it explodes and this is the runaway. But if it is smaller than 1, it's still stable. It's not that it's not stable. It is stable, but this number now is smaller than 1, so the temperature change will be larger than would have been expected in open loop, and the same thing goes for the current. The current will be actually larger than expected from just the datasheet and open loop. However, this K will be very small because you see the difference here is very small. So this number is going to be very small. I'm not going to put in numerical values. So consequently, although there will be sort of some increase in the temperature and the current as compared to the open loop situation, this is a very small change. So luckily, we don't have a big problem, even though we have here positive feedback. So what are the conclusions here? Parameter spread will cause uneven current sharing, no question about that. MOSFET and IGBT have in practice negative feedback that helps reduce the current deviation. And this is except for the case of the positive, which is really negligible because of the very low value of this coefficient. And then the key parameter for current equalization is the loop gain. Okay, this value here. If it is small, then the feedback does not make a big difference, and you can calculate the delta I and delta T from open loop consideration. So this brings me to the end of this presentation. I thank you very much for your attention. I hope you found it of interest and perhaps it will be useful to you in the future. Thank you very much.